So most of you probably noticed that if you plug in 2, you get something that means we have to do more work, right? If I plug in 2, I'm getting the square root of 9 minus 3 over 4 minus 4, which is, oh yeah, 0 divided by 0. We talked a lot last time about how 0 divided by 0, technically it's called an indeterminate form, meaning it can be anything, but what that really means for us is you have to do something. Either factor, or multiply by a conjugate, or as we'll see in a minute here, get a common denominator. Those are the 3 typical algebraic methods of dealing with a 0 over 0 type of thing. It's not the only way to deal with a 0 over 0, but 0 over 0, that means do something, do more work. Because there's usually an answer that's a number. So in this case, when you see a square root, almost all the time, if you have a 0 over 0 limit, that means we're going to multiply by the conjugate of the radical thing. And the conjugate is just the same thing, except we change the middle connecting sign. So the conjugate of the square root of x plus 7 minus 3 is the square root of x plus 7 plus 3. So we're going to do the limit as x approaches 2 of the square root of x plus 7 minus 3 over x squared minus 4 times the square root of x plus 7 plus 3 over the same thing, the square root of x plus 7 plus 3. Because we're only allowed to multiply by 1, right? We can't change the value of this. I'll point out, technically, if you plugged in 2 for x over here, you'd have square root of 9 plus 3 over square root of 9 plus 3, which is 3 plus 3 over 3 plus 3, which is 6 over 6, which is 1. So we're just multiplying by 1, but it's going to make it easier to see what's happening here. Probably is going to allow us to cancel out some problematic factors. So let's look at the denominator first. The things that aren't conjugates, we don't want to multiply them out. We want to just leave them as is. Well, we're going to do a little bit more with this x squared minus 4 in a minute. But for now, we're just thinking of this as x squared minus 4 times the square root of x plus 7 plus 3. In the numerator, that's where we actually want to multiply it out. I know I've said in the past I don't really want to multiply that, but I'll show you this one time. But what we know we're going to get should be the square root of x plus 7 squared minus 3 squared. So we should get x plus 7 minus 9. But let's show the long way. Technically, doing this the long way, it's the square root of x plus 7 times the square root of x plus 7. And then 3 times the square root of x plus 7. I've done this, I did that. And then minus 3 times the square root of x plus 7. And then minus 3 times 3. We shouldn't show all this work because the positive 3 root x plus 7 and the negative 3 root x plus 7 add up to 0. So what are we left with? We're left with the limit as x approaches 2 of, on top we have the square root of x plus 7 times the square root of x plus 7 is x plus 7 minus 3 times 3 is 9. And on the bottom here, I do want to do one thing. So we know that plugging in 2 is a problem. That means we'd like to see some x minus 2s as factors. Whatever your problem value you're plugging in is, you really want to see x minus that number as a factor so we can cancel it out. Specifically, the x squared minus 4, I should factor as x minus 2 times x plus 2. Then the square root of x plus 7 plus 3. Hey, look, that difference of squares factored as conjugates. X minus 2 times x plus 2. Those are conjugates also. Simplifying, one more step, sure. I probably could have done this here, but x plus 7 minus 9 is x minus 2. And in the denominator, we still have x minus 2 times x plus 2 times the square root of x plus 7 plus 3. And then we get to say that x minus 2 divided by x minus 2 is equal to 1. So we're going to rewrite this as the limit as x approaches 2 of 1 divided by x plus 2 times, that's a 7, not a 3, the square root of x plus 7 plus 3. Now, since we've canceled the problematic factor that was making it 0, right? Plugging in 2 here, you get 0. Plugging in 2 here, you get 0. We no longer have that 0 over 0. Now is an excellent time to at least check and see, can we just substitute in what x is approaching to get a final real value? And we can. We substitute in x equal to 2. We're going to get 1 divided by 2 plus 2 times parentheses the square root of 2 plus 7 plus 3, which ends up being 1 over 4 times 6, which is 1 over 20. Couple notes. One note is that we keep writing the limit as x approaches 2 every single step until we actually plug in the 2 for the x's and we no longer are writing the letter x, right? So up until this last step, we're writing the limit as x approaches 2 every time, and then we're plugging it in. If you don't write the limit, it changes the meaning, right? You're just saying, here we're asking a question. What is this function getting closer and closer to as x is closer and closer to 2? If you don't write the limit part, it means you have a function and you're not really asking anything about it. So make sure you write the limit every time until the last step. I thought I saw a hand over here, but it was, yeah. Well, yeah, well, I should ask which square roots, the ones here or the ones here? These ones? So those added to 0 because, and this always happens when you multiply conjugates together, the middle terms are always going to be the same except opposites. So the positive 3 times the square root of x plus 7 and the negative 3 times the square root of x plus 7, those add together to 0. And that's always going to happen. Yeah. When you say all cancel out, what do you mean? Sure, and the reason that cancels out the square is because what you've got right there, right, that square root of x plus 7 times the square root of x plus 7, well, when you multiply something by itself, that's the same as squaring. Like 5 times 5 is 5 squared. And the square root of x plus 7 times the square root of x plus 7 is the square root of x plus 7 squared, which ends up being just x plus 7. The same kind of things happening here. I could have written, instead of writing 3 times 3 here, I could have just written minus 3 squared, right? That would be the same thing. 3 times 3 is 3 squared. But the minus sign is still living out in front of that, right? It is specifically minus 3 times 3, which is minus 9, or minus 3 squared. But the squaring is happening before the subtraction is happening. All right, there's one more kind of algebraic thing we do with 0 over 0 types of limits typically. Let's look at this example. Sure. The limit as x approaches 3 of 6 over x minus 2 over x minus 3. Put some numbers on these things. Not surprisingly, if we were to plug in 3 for x, on top we'd get 2 minus 2, which is 0. On the bottom, we get 3 minus 3, which is 0. So we've got problems. Got 0 over 0 means we've got to do something. And in this case, what we're going to do is, since we have fractions in fractions, we're going to get a common denominator for those fractions that are in the numerator, or I should say the fraction. So we're going to rewrite this as the limit as x approaches 3. We have 6 over x minus, I'm going to think of that 2 as 2 over 1, and I'm going to multiply that by x over x so I can get a common denominator and actually subtract those fractions. The denominator is just going to hang out. So now we're going to simplify. We're going to rewrite this as the limit as x approaches 3 of 6 over x minus 2x over x, or just 6 minus 2x all divided by x. That's the whole point of getting a common denominator, so that we can actually subtract those fractions and get one fraction in the numerator divided by x minus 3. Right? This part here, this top part here, that's just 6 over x minus 2x over x. Since they have the same denominator, we can just subtract the numerators and leave the denominator as is. Here's the part where people often feel like I'm doing something tricky. So whenever you have something divided by something else, that's the same as multiplying by a reciprocal, right? 10 divided by 5, which is 2, is the same as 10 multiplied by 1/5, which is also 2. So instead of saying we're dividing by x minus 3 over 1, we're going to multiply by 1 over x minus 3. So we're going to write this as the limit as x approaches 3, 6 minus 2x over x multiplied by the reciprocal of x minus 3 over 1, which is 1 over x minus 3. When you have fractions multiplied by fractions, we just multiply the tops and bottoms together. So it's going to be top times top, bottom times bottom. I am going to do one extra thing here. So notably, I have x approaching 3. What kind of thing am I looking to make cancel out? X minus 3, right? The x minus 3 is the problem, because 3 minus 3 is 0. So I really, really, really hope to see an x minus 3 in the numerator and the denominator. I have it in the denominator already. That's great. So that tells me I shouldn't multiply out the denominator. I shouldn't write it as x squared minus 3x. I should just write it as x times x minus 3. On the other hand, the numerator, I would like to factor something out so I also get an x minus 3. I could factor out a 2, but the better choice would actually be to factor out a negative 2. So if I factor out a negative 2 from the 6 minus 2x, 6 divided by negative 2 is negative 3, and negative 2x divided by negative 2 is positive x. And I don't need to write the 1 in top because it's still there, right? It's right. And now, even though I've written these kind of out of order, those are the same thing. Negative 3 plus x and x minus 3 are the same. You can rewrite it if you want to, right? We could totally rewrite this as the limit as x approaches 3 of negative 2 times x minus 3 over x times x minus 3. But it's really not necessary to do that unless you really, really want to. These divide to 1. So we're left with the limit as x approaches 3 of negative 2 divided by x. And now we can plug in 3 for x and get negative 2/3. That's our limit. So when we see a 0 over 0 type of limit and there isn't something else going on, it's kind of just algebraic terms like powers of x, square roots of x, things like that, fractions of x. Usually a 0 over 0 limit, one thing we do is we like to say we do algebra. And the algebra could be factoring and canceling. And usually there's always some amount of factoring and canceling, even if you do these other two things first. Or first multiplying by a conjugate, if there's a radical, or getting a common denominator if you have fractions in fractions. And again, these second and third things we do often then lead back to the first thing, which is still some factoring and canceling. So I want you all to try this next one on your own. We'll define, say, the limit as x approaches, sure, 8 of, yeah, sure. 4 over x minus 1/2 divided by x minus 8. And I would suggest starting by getting a common denominator in the numerator here by multiplying the 4 over x by 2 over 2 and the 1 over 2 by x over x. Start writing out the first step. You should feel free to work ahead. Oh, I should check. Is it a 0 over 0? Yes, it is a 0 over 0. 1/2 minus 1/2 over 8 minus 8. Yeah. There are the steps I have so far. We've gotten the common denominator in the numerator by multiplying 4 over x by 2 over 2 and 1 over 2 by x over x. That became 8 over 2x. Sorry, I should say the limit as x approaches 8 of 8 over 2x minus x over 2x, all still divided by x minus 8. And then we can simplify the numerator by subtracting those fractions together, making it one fraction, and having the limit as x approaches 8 of 8 minus x over 2x divided by x minus 8. And then I threw in an over 1 there because the next step we're going to flip and multiply. So we're going to rewrite this as the limit as x approaches 8 of 8 minus x over 2x times 1 over x minus 8. And you could, if you wanted to, put it in one fraction. You probably don't need to write this step, but I always like to write it like this, just as one fraction, 8 minus x over 2x times x minus 8. Now, we kind of saw this in the last one, but it was a little bit easier to deal with because you can factor out a -2. But here we have 8 minus x divided by x minus 8. And I think I might have talked about this a little last time, but I don't remember exactly. So here's what I like. If you pick any number that isn't 8, and just look at the 8 minus x divided by x minus 8 for a second, I'm going to pick 5. 8 minus 5 is 3. 5 minus 8 is -3. And 3 divided by -3 is -1. What if I picked a different number? What if you pick 2? We get the same thing, right? 8 minus 2 is 6. 2 minus 8 is -6. 6 divided by -6 is still -1. Any value you pick for x other than 8 is going to give you a number divided by the negative of that number, which is going to be -1. So when you subtract things in the opposite order, you can say, well, that's going to always divide to -1. If you don't like that, that is okay. You can take a slightly longer route and say, well, I really would prefer just to factor out a -1 from the numerator and rewrite it as the limit as x approaches 8 of, in the numerator, -1 times -8 plus x divided by 2x times x minus 8. -8 plus x is the same as x minus 8, so those do divide to 1. So we're left with the limit as x approaches 8 of -1 over 2x. And then we plug in, we no longer write the limit. We get -1 over 2 times 8, which is -1 over 16. Yes.
Why do you no longer write the limit?
So because we're no longer taking the limit. So at this juncture, I'm still asking, what value is this expression getting closer and closer to as x is getting closer and closer to 8? And now I'm saying, oh, the answer to that question is -1/16. We are saying that as x gets really, really close to 8, this function gets closer and closer and closer to -1/16. But we've essentially, another way of viewing it is, we've done what the instructions told us to do, right? The instructions said take the limit, and we did, so we no longer write those instructions. All right. So, yes. Not 2.8, 2 times 8. That's a 2 multiplied by, I substituted in for x a value of 8. Sometimes we use a dot to represent multiplication, but right, it's not down here, it's in the middle. So there's 2 other types of 0 over 0 limits I want to briefly mention. So I think I'm going to wait on one of them. But there is one other type that can be, unfortunately, a little bit more problematic. So let's say we have, sure, I like this one. The limit as x approaches 6 of, let me see, how did I do this before? Yeah, sure. The absolute value of x minus 6 divided by 2x minus 12. Which, as you might have guessed, is going to be a 0 over 0 type. Now, the problem is there isn't really there isn't really factoring canceling we can do until we deal with the absolute value. And the problem with the absolute value is it's actually defined as a piecewise function. So here's what I want you to think about for a second. The absolute value of x minus 6, well, you could graph it. It looks like your usual absolute value function, which is the V shape, but it shifted 6 to the right. I think, right? To the right? Yeah, it's to the right, because x has to be 6 bigger. So the graph looks like this. We shifted the bottom of the V over to 6. Looks like that. Another way to think about this is that the absolute value of x minus 6 is going to equal. So what if x was, say, 10? 10 minus 6 is 6. Let's try that again. 10 minus 6 is what? 4. And the absolute value of 4 is still 4. So if x is bigger than 6, the absolute value of x minus 6 is just going to be x minus 6. Which seems reasonable, right? This part of the line, or sorry, this part of the graph certainly looks like the line y equals x minus 6. But what if x was, I don't know, 1? The absolute value of 1 minus 6 is the absolute value of negative 5, which is equal to negative 5, or 5. Right, but that's how you turn a negative into a positive, is you multiply by negative 1. So if x happens to be less than 6, then you get the negative of the stuff you had inside the absolute value. Which again, looking at the graph, seems pretty reasonable. This part of the absolute value function looks like the line y equal to negative parentheses x minus 6, or distributing the minus sign, negative x plus 6. So that's what we're going to have to do to see what this limit is. We're going to actually have to break this up into 2 limits where we look at the right side and the left, the right side and the left side of 6. So here's what I mean. We're going to look at the right-hand side limit by doing the limit as x approaches 6 from the right of the absolute value of x minus 6. Let's factor the bottom as 2 times x minus 6. We can't cancel anything yet, but now we're just going to say, oh, cool. X is bigger than 6, which means the absolute value is just equal to x minus 6. So we're going to rewrite this as the limit as x approaches 6 from the right of just plain old x minus 6 divided by 2 times x minus 6. The x minus 6's divide to 1. So we're left with the limit as x approaches 6 from the right of 1/2. And the limit of a constant is just that constant value. Okay, the right-hand side limit is 1/2. The left-hand side limit is a different animal. We look at the limit as x approaches 6 from the left of the same thing. Absolute value of x minus 6 divided by 2 times x minus 6. Now, since x is less than 6, we have to use this piece of the piecewise function. So this is equal to the limit as x approaches 6 from the left of negative parentheses x minus 6 divided by 2 times x minus 6. The x minus 6 is still divided to 1, but that means we're left with the limit as x approaches 6 from the left of negative 1 over 2. And again, the limit of a constant is just that constant, which is negative 1/2. And the right-hand side and the left-hand side aren't the same, which means the overall limit doesn't get to exist. So in this case, we would say that the limit as x approaches 6 of the absolute value of x minus 6 divided by 2x minus 12 does not exist. And you could even say more. You could say because the limit as x approaches 6 of x minus 6 in absolute value over 2x minus 12 from the left does not equal the limit as x approaches 6 from the right. Although I feel like that's probably writing too much. Sometimes you get a 0/0 limit like that, and the only way to deal with it if it's an absolute value is break it up into a right-hand side and left-hand side. But it's a little bit gnarly.
But we could use type logs, it does not exist.
So for a limit to exist, both the right-hand side value and left-hand side value have to be the same. But we have a right-hand side value of positive 1/2, and a left-hand side value of negative. You could also graph this thing. It's interesting if you graph the function. Sure, I can make. Let's give myself some more room here. So I want to point out that the graph of f of x equal to the absolute value of x minus 6 over 2 times x minus 6. All right, everybody pick a number bigger than 6 in your head. Plug it in. What'd you get? I got 1/2. I plugged in 9. I got 9 minus 6 is 3 over 2 times 9 minus 6 is 2 times 3. And the 3's canceled, and I got 1/2. Did you do it when you plugged in 10? You get the same thing, right? 10 minus 6 is 4. 10 minus 6 is 4. 4 divided by 2 times 4 is going to be 1/2. Any number you pick bigger than 6 will give you an output of positive 1/2. So if we try to graph this thing, over here at 6, any choice bigger than 6 will give you a y value of 1/2. Any choice smaller than 6, say like 2, is going to give us a value of negative 1/2. Because if you plug in 2, I'll point out that f of 2 is the absolute value of 2 minus 6 over 2 times 2 minus 6. The absolute value of negative 4 is 4, still divided by 2 times negative 4. And the 4 divided by negative 4 is negative 1. That gives me a negative 1/2. So on the other side, the left side of 6, the y values are all negative 1/2. And so you can see that from the right and the left, we're not getting close to the same y value, which means the overall limit doesn't exist. But if someone asked you to show this, they would probably want you to do something more like this.
So anytime you're prompted with the absolute value, you find it.
Typically, I wouldn't say always. So I should say, yes, if it makes sense to. But someone else could ask you a totally different question that would feel like kind of unkind. No. So I could also say, what's the limit as x approaches 19 of the absolute value of x minus 6 over 2x minus 12? Well, in this case, what should I do? Just plug it in, right? If you plug in 6, you get 0/0. Plug in something else, you're just going to get probably a half or negative a half. And let's see, plug in 19, get the absolute value of 19 minus 6 over 2 times 19 minus 12, which is going to be 13 divided by 26, which is, it's 1/2. So, right, so with absolute values, yes, if you're approaching a 0/0 kind of thing, yeah, you typically have to look at the left and right hand side. Okay, so let's continue talking about limits, but we're going to move on from limits that are 0/0 type. You'll certainly see it in a fair number of them, especially when we roll back around to talking about the limit definition of the derivative. That's a lot of the reason why we've talked about 0/0 limits, but there are other limits to look at as well. So let's go ahead and look at something like, where'd you go? Yeah. The limit as x approaches 4 from the right of, 5x minus 11 over x minus 3. I'm numbering suspect here. That is. Don't worry about the numbers. I try to pay them. Should be a 5. So, following our usual kind of ways of dealing with limits, the first thing we should do is plug it in. If I plug in 4, let's see what happens. I get 5 times 4 minus 11 over 4 minus 3, which is 9/1. Cool, we're done. And we're done because I picked the wrong number to approach the right-hand side from. That's okay. Sometimes people make mistakes and it ends up being an easy question. Great, take the win. So now, what we really wanted to do was the limit as x approaches 3 from the right of 5x minus 11 over x minus 3. Now if we plug in 3, we're going to get 15 minus 11 over 3 minus 3, which is 4 over 0. 4 over 0 is not an indeterminate form. It doesn't just get to be anything in the whole wide world. There's only really 2 or 3 technically possibilities here. This limit is either going to be really, really positively large or really, really negatively large. And in this case, since the numerator is positive and the denominator is 0. But technically we were approaching 3 from the a little bit bigger than 3 side. So this x minus 3 or this 3 minus 3 is really a number a tiny bit bigger than 3 minus 3. Means we're getting a slightly positive denominator, which I like to write with a 0 superscript plus. So really you have 4 divided by a very, very tiny positive number, which is going to be a very, very large positive number. One thing I want to point out, and I say this a lot, is when you have fractions, when you divide by a big number, your fraction gets small. Right? 4 divided by a billion is 0.00000 something. On the flip side, if you have a fraction and you're dividing by a very, very small number, your fraction gets gigantic, blows up. You can see this if you want by saying, well, what's 4 divided by 1/1,000,000th? Right? 1/1,000,000th is certainly a very small number. It's 0.000001. Probably missed a 0 there, whatever. But if you divide this here, well, how do you divide by a fraction? You flip and multiply. So this is really the same as 4 times 1,000,000 divided by 1, which is 4 times 1,000,000, which is 4 million. And that's pretty big as far as numbers go. So when you divide by something big, your fraction gets small. When you divide by something small, your fraction gets big. When I say small, I mean 0. When I mean big, I mean positive or negative infinity. So this limit would be positive infinity. This expression is getting super duper large as we get close to 3 from the right hand side. And the second we'll say something graphically. Let's look at the other side of 3. The limit as x approaches 3 from the left of 5x minus 11 over x minus 3. Well, again, we're going to plug in. On top, we're still going to get 15 minus 11, which is 4. In the denominator, we're going to get a number slightly less than 3 minus 3. So if we have a number that's smaller than 3, like 2.999, and we subtract 3, we're going to get a very, very small negative number. So this is going to look like 4 divided by a very small negative number, and a positive divided by a negative should be negative overall. So this is going to be negative infinity. Here's what this means graphically. If we were going to graph f of x equal to 5x minus 11 over x minus 3, we're not going to graph the whole thing, but I will point out that at x equal to positive 3, we have a vertical asymptote. And specifically, from the right-hand side of 3, the graph is going up to infinity. So it's going to look something like that. And from the left-hand side of 3, the graph is going down towards negative infinity. So do something like that. So that's what it means when you have a limit as x approaches some not infinity number, and but the answer ends up being either infinity or negative infinity. That means you have a vertical asymptote at that x value. And as long as one of the sides goes to infinity, you have a vertical asymptote. Usually both go to some sort of infinity, but it's possible to have just one side go to infinity, the other side go to like 2 or something. So vertical asymptote at 3, because our limit is blowing up. Our function is getting super duper large or super duper negatively large. The sum up here is that when you have a limit, you plug it in and you get some non-zero number divided by 0, you only have 2, I'll say the third thing in a second, things that can happen. You either get infinity or negative infinity. The third thing that can happen is if they ask for the double-sided limit. If I said, what's the limit as x approaches 3 of 5x minus 11 over x minus 3? Well, since the right-hand side limit and the left-hand side limit are going in totally opposite directions, the double-sided limit doesn't exist. So those are the 3 things that can happen when you have a non-zero divided by zero type of limit. You can either get infinity or negative infinity, or potentially it does not exist if it's a double-sided and they go different directions. And those are the only things that can happen with not zero divided by zero. Let's look at one or two more and we'll see. Yeah. Yes. So literally, so for the limit to exist, so I should point out, technically all of these limits don't exist. Right? That first limit, we're saying it's infinity, but that means the function's getting larger and larger and larger and larger and larger as x gets closer and closer to 3 from the right-hand side. Sorry. But that means limit doesn't exist, right? That function is not getting close to one specific number, just growing. But we're going to be more specific and say, okay, yeah, it doesn't exist, and we know it gets super. On the other side, same thing, right? From this side, limit doesn't exist, but it's getting super duper negatively large. But if you're looking at the double-sided limit, for it to exist, or for us to say something, both sides have to do the same thing. Since one side's going this way, one side's going this way, we say that the overall double-sided limit can't exist because they're not going in the same direction. We'll look at a different example here to see how they can exist. So let's say we had, yeah, sure, the limit as x approaches 2 of x minus 5 over 2 minus x squared. Oh, can't say that, sorry. And I'll point out if we plug it in, we're going to get -3 divided by 0. Since we don't know which side of 0 we're on, right, because we didn't just do a right-hand side, left side, to look at the overall double-sided limit here, we really have to look at the left side and the right side. So let's look at the right side first. So the limit as x approaches 2 from the right of x minus 5 over 2 minus x squared. So I'll remind you, we are just going to plug in actually 2, not 2.1 or 2.5 or something a little bit bigger than 2, actually 2. So we're going to get 2 minus 5 on top. On the bottom, we're going to get 2 minus 2. And I'll point out, it is a number slightly larger than 2. And 2 minus a number a little bit bigger than it is going to be slightly positive or negative? It's going to be negative, right? It's 2 minus a number bigger than itself. So it's going to be a slightly negative number squared. But anything squared turns out to be positive. I should say any real number squared is going to be positive. So what we really have here is a -3 over a very small positive number. And then negative divided by a positive is going to be negative. Infinity. Again, right? We're dividing by a small number, so our fraction is blowing up. On the other side of 2, on the left side of 2, if we take the limit as x approaches 2 from the left-hand side of x minus 5 divided by 2 minus x squared, similar thing's going to happen. We still have -3 on top because 2 minus 5 is -3. And in the denominator, in the parentheses, 2 minus a number a little bit smaller than 2, like 1.999, is going to be slightly positive. And squaring it will keep it positive. So here we have -3 over a positive 0, which is going to still be a negative over positive, so it's going to be a negative infinity. And in this case, since the left-hand side limit and the right-hand side limit are both going towards the same type of infinity, we would also say that the double-sided limit is also a limit value of value. The limit is negative infinity. So we would say, so yes, the limit as x approaches 2 from both sides of x minus 5 over 2 minus x squared is also negative infinity because those two are both. I'm trying to avoid saying that this limit exists because technically it does not. Since the left-hand and the right-hand side limits are going towards the same infinity, we would also say that the double-side limit goes to the same infinity. What else? That's really all there is to limits where you have not 0 divided by 0. So I'll just point out if you have the limit as x approaches a of some f of x, and it ends up being a not zero divided by zero, you plug it in, there's only three options: infinity, negative infinity, or does not exist. Those are the only things that can happen. One more example for you. Let me see. Let me try to do this the right way. Let's see. Let's say the limit as x approaches, sure, pi over 2 from the right-hand side of tangent of x. Well, first of all, it's not even a fraction. So I guess I should rewrite it so it is a fraction. So that's going to be the limit as x approaches pi over 2 from the right of sine of x over cosine of x. And if we plug it in, we get sine of pi over 2 divided by cosine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So it's going to be some sort of infinity. So here's the hard question. Is my denominator a little bit positive or a little bit negative? This one gets really kind of tricky because if you look at the unit circle, we're up here at an angle of pi over 2. And over here on this side in quadrant 1, cosine is positive. And over here on this side, cosine is negative. So if we're approaching pi over 2 from the right-hand side, which side are we on? Quadrant 1 side or the quadrant 2 side? Well, it's kind of a trick. Because if you think about it directionally, you're like, well, James, you said you're coming from the right-hand side, so it should be over here in quadrant 1, but it's not. Because the right-hand side really means the bigger than that number side. And in this context, the angles get bigger as we go around counterclockwise. So this side over here is where the angle is bigger than pi over 2, and this side over here is where the angle is between 0 and pi over 2. So technically, we're in quadrant 2 where cosine is slightly negative. So we're going to get negative infinity. I would also point out that if you look at the graph of tangent of x, you do get vertical asymptotes of pi over 2. Never have enough room to throw in a graph here, sorry. So just for more context here, the graph of tangent of x has asymptotes at pi over 2 and at 3 pi over 2 and at negative pi over 2. I should say vertical asymptotes. And looks a bit like this. So you can see that, oh yeah, if we come at pi over 2 from the right-hand side, the graph is going down to negative infinity. Whereas if we'd asked for the limit as x approaches pi over 2 from the left-hand side, it would have been positive infinity. Kind of interesting. Not that interesting. Okay, so again, that's really most of all there is to say about limits where you get not 0 divided by 0. Not much happens other than getting infinity or negative infinity or does not exist. Let's circle back around now to limits that where x is approaching infinity, because we kind of talked about limits to infinity where like the variable is approaching infinity when we talked about sequences, right? We wanted to find what the sequence converged to by taking the limit as n goes to infinity. Now we're going to kind of do the same thing, but with some x instead of n. It's really the same work, but our functions are going to get a little bit funkier. Let's see, and where did I put you guys? I know where I go over. Sorry, 1 second. Got things all over the place, you know, typically. Yeah. See, are you the ones? Sure. So let's look at a few examples here that are similar to many of the homework problems I've been seeing. So let's say we want to find the following. The limit as x approaches infinity of 6x squared plus 5 over 2x squared minus 3x plus 1. I think you could all show me on your fingers what the answer to this limit is. Yeah. because you are seeing that the numerator and the denominator have the same degree, which is 2. So the limit is the quotient of those leading coefficients, which is 6 divided by 2, which is 3. And the same is true whether it's to infinity or to negative infinity. If we want to find the limit as x goes to negative infinity of 9x squared plus 4x plus 1 over 7x squared plus 3x plus 2. Same sort of deal. You can't show me on your fingers this time, but you know what the answer is going to be. It's going to be 9 over 7. I don't know at this juncture how much work your instructors expect to see. I would imagine on your first exam, they probably still want to see more work than just that. They probably want to see you divide everything by x squared or factor out an x squared. So we'll do that for the next one. See what yeah.
I'm just curious, it has to be infinity or negative infinity to apply that rule.
Correct. That is an excellent observation. I want to make sure everyone heard that. To apply that rule, it has to be going to infinity or negative infinity. It does not work if you've got like x approaching 3 or something that makes it 0 over 0. So yes, that's only for when x is getting really, really big or really, really negatively big. Yeah, let's look at something like this. Limit as x approaches infinity. Let's see which way I want to go here. Yeah. Yeah, I like that. 5 plus 8x to the 4th over 2 minus x cubed. Okay, well, that's a whole world of grossness. If you were to plug it in, the top would be getting infinitely large. The bottom would be getting negatively infinitely large. So you'd have infinity divided by negative infinity. And just like 0 over 0, that's something that requires more work. This is also called an indeterminate form. It can literally be anything. It was before, right? This infinity over infinity was 3. That infinity over infinity was 9 over 7. This infinity over infinity is going to be something else. Let's see what we get. So here I am going to show the work. And I think I did this wrong last time I did it. Or at least I did it the way, I didn't do it wrong, but I did it in a way where it could have been ambiguous. When you're doing rational rational functions and x is going to infinity or negative infinity, we typically want to divide by the highest power of x in the denominator. So I want to divide everything by x cubed, not by x to the 4th. It's still plausible to divide by x to the 4th. It's just you run the risk of making it harder to do. So we divide everything by x cubed. We get 5 over x cubed. 8x to the 4th divided by x cubed is going to be 8x. 2 over x cubed is 2 over x cubed. And x cubed divided by x cubed is 1. So we divided everything by x cubed. And now we take the limit. We do it all at once, though. So the 5 divided by x cubed is going to get really, really small. The 8 times x is going to get really, really big. The 2 over x cubed also small, and the minus 1. So overall, the numerator is gigantic, and the denominator is -1. And a really big number divided by -1 is a really big negative number. So we're going to get negative infinity here. The top is a lot bigger than the denominator, but the overall sign is negative. And that makes sense because the degree on top is larger than the degree on the bottom. So it would make sense that the numerator is growing faster than the denominator, and your fraction continues to get larger and larger and larger and larger. It just happens to be negatively larger and larger and larger. Let's look at the other side. The limit as x approaches negative infinity of the same thing. 5 plus 8x to the 4th over 2 minus x cubed. Well, again, if we did the same work, we would write it as the limit as x approaches negative infinity of 5 over x cubed plus 8x over 2 over x cubed minus 1. 5 over x cubed still goes to 0. 8 times x now is going to be 8 times negative infinity, which is going to be negative infinity. The denominator is still 0 minus 1. So now we have negative infinity divided by -1, which is positive infinity. Which kind of makes sense if you think about like the overall like highest terms, these things. Your highest term here is like 8x to the 4th. Your highest term here is like negative x cubed. And 8x to the 4th divided by negative x cubed simplifies down to just -8 over, sorry, negative 8 times x. And if x got really, really big, you'd have a negative infinity. And if x got really, really negatively big, you'd have a positive infinity. That's kind of what's going on there.
Why don't you set x to power 3 as x to power 4?
Good question. So sometimes it works out perfectly fine to use the x to the power 4. Let's see what happens if we did it. So we tried the limit as x goes to infinity, and we took this expression and divided by x to the power of 4. We'd have 5 over x to the 4th plus 8 over 2 over x to the 4th minus 1 over x. So here's what's going to happen. On top, we're going to get 0 plus 8, which is 8. On the bottom, we're going to get 0 minus 0, which is 0. But here's the issue. I don't know if my denominator is slightly positive or slightly negative. So I don't know if my answer should be negative infinity, which is what it should actually be, or positive infinity, which it shouldn't be. So that's the whole reason why you divide by the highest power in the denominator, to avoid this ambiguity where you're not sure of the sign of the denominator. And it's really unclear here. I don't know if the denominator is slightly positive or slightly negative writing it this way. I'd have to do a lot more work, expend a lot more effort, where it's much, much easier just to divide by the highest power in the denominator instead. So thank you for asking that question. It's a really well-timed thing to say. Yes, we always want to, if we're dealing with limits to infinity or negative infinity, and it's a rational function, you essentially want to divide by the thing that's growing the fastest in the denominator. And I phrase that very specifically because these next examples look a little different, but they still kind of work the same way. So let's say we had something like, where'd you go here? Yeah. Something like the limit as x approaches infinity of 5e to the 4x over, 6e to the 3x minus 2e to the 4x. So, of the two things, e to the 3x and e to the 4x, which is the thing that's growing faster? Well, probably the one with the bigger x. And it is. If you graph e to the 3x and e to the 4x, e to the 4x is steeper as you move to the right. So in this thing here, e to the 4x is growing the fastest. So we're going to divide everything by the thing that's growing the fastest that's in the denominator, which is e to the 4x. So we're going to rewrite this as the limit as x goes to infinity of 5e to the 4x divided by e to the 4x over 6e to the 3x divided by e to the 4x minus 2e to the 4x divided by e to the 4x. Simplifying, limit as x goes to infinity of, on top we have 5. On the bottom, so this term here, here's what I'm going to say about this, and this is going to hold for the next part too. I want to simplify this in a way so that my exponent is being raised to a positive power. So in this case, my e to the 3x divided by e to the 4x, I want to write that as an e to the x in the denominator. I want to write that as 6 divided by e to the x, not as 6 times e to the negative x. Either way technically will work out fine, but I have a preference, and I like doing it that way better. And then over here we have minus 2. And then if we let x go to infinity, e to a really big number is still really big, and 6 divided by a really big number is going to get closer and closer to 0. So that part's going to go to 0, and we're going to be left with 5 over negative 2, or negative 5/2. Okay. We have to be even more careful when we go the other way, meaning if we look at the limit as x approaches negative infinity of the same thing. This is where I think things get tricky. So if you go towards negative infinity, what's e to the negative infinity? Well, what's the graph of e to the x look like? If you go to the left, the graph of e to the x gets closer and closer to 0. So things aren't actually getting infinitely large here. But if you plug in negative infinity, what you're going to get is 0 divided by 0 minus 0. So it's still an indeterminate form. we still have to do something. So instead of dividing by the thing that's growing the fastest, because none of them are really growing, we're going to divide by the thing that's getting small the slowest, or not going to zero as fast. In other words, you're going to divide by everything by e to the 3x, because that thing is going to be the bigger of the two things as we go that way. Just as a point here, I'll try to graph it. So it's not going to look pretty, but here's your e to the 4x. And so that's e to the 4x in red. And here's your e to the 3x in purple. Right, so to the right, e to the 4x is growing faster. To the left, e to the 4x is declining faster. And e to the 3x is not. It's declining slowly. So it's the bigger thing. So if we divide everything by e to the 3x, let's see what happens. We get the limit as x goes to negative infinity of 5e to the 4x divided by e to the 3x over 6 e to the 3x divided by e to the 3x minus 2 e to the 4x divided by e to the 3x. So we're going to get the limit as x goes to negative infinity of, let's see. On top, we have 5e to the x. On the bottom, we have 6 minus 2e to the x. Now, personally, I don't like to write it like this, because for me, it's taken many, many years of practice to remember that e to the negative infinity is essentially going to 0. I find it much more helpful if I write it so that my powers all end up being positive when I plug in the thing x is approaching. So I would much rather write it, even though it's going to feel like it might be more complicated this way, I think it helps me write it as 5 over e to the negative x, and then on the bottom 6 minus 2 over e to the negative x. Because then if I plug in a negative infinity, e to the negative infinity is e to the positive infinity, which is super duper big. And then 5 divided by a really big number goes to 0. And 2 divided by a really big number goes to 0. So we end up getting 0 divided by 6 minus 0. And 0 divided by 6 is just 0. Kind of funky. It's really funky, actually. But that's what I say is, if you have limits like this, where you have like limit to infinity or negative infinity of e to the something, when you're going to infinity, you want to divide everything by e to the biggest thing that's in the exponent, that's in the denominator. And when you're going to negative infinity, you have to divide by the smaller thing, e to the smaller thing. That's the way to make this work. It's a little tricky. It takes practice. What else have I got here? Sure. Oh yeah, one other one I'll talk about, and then yeah, we should talk about it. Okay, so let's see here. The other thing I'll mention is, well, first of all, there's some notation things I just want to make sure everyone's aware of. So I've noticed this limit a few people have asked me about. The limit as x approaches infinity of exp of bracket -9 natural log of x. What is ex? Oh yeah, question. What does exp mean? Yeah, it means next one. Specifically, exp, what this means is e to the stuff in the bracket. E to the power of whatever's in the bracket. It's just notation that makes it easier to write it out. Like if you're typing stuff, it's much easier to type exp bracket than it is e to the thing. So it's really just some notation someone came up with to make it easier to write this thing at some point. So if it were me, I would rewrite it. I would rewrite this as the limit as x goes to infinity of e to the -9 natural log of x. Just because that way of writing it makes more sense to me. There's two ways you can approach this. One way would be to say, well, what's going to happen if I let x get really, really big? Well, if x gets really, really big, the natural log also gets really, really big. Very slowly, but still big, right? The graph of natural log of x looks like that. And even though it's slowing down, it's still increasing forever and ever and ever, right? It just keeps getting bigger and bigger and bigger and bigger and bigger. So this natural log of x does get infinitely large. And then you multiply by -9, and we're getting negatively infinitely large. Or as James would prefer to write it, the limit as x goes to infinity of 1 over e to the positive 9 natural log of x. I really like my exponent to be positive when I'm plugging in whatever x is approaching. So now I can be like, oh yeah, this is getting big, 9 times big, and e to a big number is a big number, and then dividing by a big number means we're getting closer to 0. Or you can do something completely different, which is going to make it hard to do the second part. But the other thing you could do is say, hey, I know how to simplify this. E to the -9 natural log of x is e to the natural log of x to the -9th. Or you can bring that -9 up as the power, and then that's going to be x to the -9th, or 1 over x to the 9th. And then you could say, cool, the limit as x goes to infinity of e to the -9 natural log of x is the same as the limit as x goes to infinity of 1 over x to the 9th, which is 0. Because again, dividing by a really big number. The problem is, for the other half of this question, it totally fakes you out. So the other half of this question is the limit as x goes to negative infinity of the same thing, exp of -9 natural log of x, or as I would prefer to write, e to the -9 natural log of x. And in this case, it will not do us to simplify this. And here's why. If you simplify this, you could justify to yourself, well, yeah, 1 over x to the 9th, negative infinity to the 9th power is going to be a really, really, really big negative number. And 1 divided by that would be 0. But there's a problem. The problem is the natural log function is only defined when your inputs are positive. So you can't even begin to think about the limit as x goes to negative infinity, because the natural log of -1 doesn't even exist, let alone the natural log of negative really big numbers. So the problem here is that you have to look at the original version. If the original version has a domain issue, that's the end of the story. So the problem here is that this part here is undefined if x is less than 0, less than or equal to 0, I should say. So the whole limit doesn't exist because you can't even begin to start plugging in x's. It would be kind of like if someone said, what's the limit as x goes to negative infinity of the square root of x? Well, that is not defined, right? You can't take square roots of negative numbers to get real results. So this limit also does not exist because the inputs are not giving us real number outputs. So sometimes the domain will be a blocking thing. It'll keep you from doing what you want. Yeah.
So you can't take the limit of a negative number.
No, I'm not saying that. I'm saying you can't take the limit of. Yes, you can't take the limit of the natural log of a negative number. That's correct. Because natural log of a negative number is undefined. This is a reminder, right? The reason the natural log of a negative number is undefined is because if I asked you, for example, let's use a different base, just to, for example, if I asked you, what's log base 2 of, let's start with positive 8, you know, my favorite example. What's log base 2 of positive 8? Everybody? 3, because 2 to the third is 8. But log base 2 of -8 doesn't work. 2 to some power is always positive. It's never going to equal -8. So that's why we can't take log base 2 of -8. We can't take natural log of a negative number. We definitely can't take the limit as x goes to negative infinity of natural log of x, because you can't have negatives as the input there. So this one does not exist. And again, I'll stress one more time, even if it simplifies something where you could do it later. For example, here's something that is going to be super annoying. The limit as x goes to negative infinity of the square root of x squared also does not exist because the inside is jamming us up. We can't take the square root of a negative number, even though if you square root a square, if you square a square root, it isn't being just x. But the thing here is that if you have the square root of x squared, you know your domain has to start off with x being non-negative. But that's a problem. This also does not exist. It's undefined. Yeah, so the main issues. Sometimes they're actually issues. All right, we should start talking about continuity in the last 12-ish minutes here. Which we've already alluded to a few times, but we should be a bit more formal about it. So, continuity. So let's look at some examples of things that are not continuous. For example, I'm gonna draw some pictures here. So here's a function that has a hole at the point where x is 2 and the y value would have been 3. So this function is definitely discontinuous at 2. It's not even defined at 2. F of 2 is undefined. Or we might have something like this, where we have a vertical asymptote at x equals 2. And here, actually, this is also discontinuous at 2 for the same reason, in that the function is not defined at 2. We're calling this f of x. Here, f of 2 is undefined as well. But that's not the only way we can be discontinuous. You could have something more like this, and we've definitely seen examples like this before, where f of 2 is defined. Maybe you have something like that. Where it certainly looks like f of 2 is equal to 3 here. But the limit as x approaches 2 does not exist. Because the limit as x approaches 2 from the left, well, as we approach 2 from the left, we're getting closer to 3. And that's not equal to the limit as x approaches 2 from the right of f of x, which is equal to 5. So the left-hand limit and the right-hand limit don't match up. If the limit doesn't exist, the function can't be continuous, right? You're going to have some sort of jump. And thirdly, kind of the case we see the least often, is you could have something that looked like this. Three. Where the function is defined, f of 2 is 5. The limit exists. The limit as x approaches 2 from either side of 2 is going to be 3. The overall limit is 3. But you can still visually look at that and see, James, that's not continuous, right? I had to lift my pen off the paper to draw that little dot up there. This is discontinuous because the function value and limit value aren't equal to each other. These are not equal. So the function is discontinuous at 2. So these are kind of all the ways we see discontinuity. Either with the function being undefined at the point, I should say, these are all the ways we see discontinuity at a particular point. Where the function isn't defined there, or the function is defined, but the limit's not defined, doesn't exist, or they're both defined and exist, but they're not equal to each other. So for the function to be continuous, function has to exist, limit has to exist, and they have to equal the same thing. I should point out, the way I've drawn all these functions, they're continuous almost everywhere. This function, this function, this function, and this function are all continuous actually everywhere except for at 2. And we would still describe them all as being discontinuous. If you're discontinuous at one point, that's the name you get. So, we will say, definition. F of x is continuous at x equal to a if and only if Now, really, this is a one-line definition, but we break it up into three parts. So I will actually point out it's kind of unnecessary to write these first two parts. I'm going to write them anyway. These three things are true. One, f of a is defined or exists, whatever you want to say. Two, the limit as x approaches a of f of x exists, which usually means checking that the left-hand limit and the right-hand limit are equal to each other. Limit as x approaches a from the right of f of x is equal to the limit as x approaches a from the left of f of x. And finally, the third part, which is technically the only part you actually need, is that they're equal to each other. The limit as x approaches a of f of x is equal to f of a. And the reason you only need this last part is because for this last part to be true, the first two parts already had to be true. For the limit value to equal the function value, they both have to be defined and exist. And then they have to be the same. So if you look at the textbook, you'll probably see the definition to be only this last part here. But when we're doing problems, it usually is easier to break it up into thinking about it as these three pieces. Where first we check to see that f of, let's say if we're taking the limit as x approaches 2, or the checking to see if it's continuous at 2, we would check, does f of 2 exist? Does the limit as x approaches 2 exist? And then are they equal to each other? And if any one of those three things is not true, we stop and say the function is not continuous at that point. So let's look at an example. Yes. Yeah, that's f of a. Those are all a's. That's an a. That's an a. That's an x. That's an x. That's an a. An x. So let's look at an example here. So our function, and most of our examples of these things that are continuous or discontinuous somewhere will usually be piecewise functions. So let's say f of x is the piecewise function x squared plus 1 when x is less than 0, e to the x when x is bigger than or equal to 0 and less than or equal to 1, and 2 minus x when x is bigger than 1. We might draw a graph of it later, but we're not going to draw a graph of it right now. So depending on who's writing this question, they could phrase it in a number of ways. The most annoying way of phrasing this question is, where is this function continuous? So a few things to say here. The only issues or problem points we need to examine really are when we change from one piece to another. So really, we're only concerned about, is this function continuous at 0? And is this function continuous at x equals 1? Because everywhere else it is continuous. If x is less than 0, the function is x squared plus 1, which is just a parabola. And any parabola, well, actually, any polynomial is always continuous wherever it's defined. And similarly, e to the x, you've seen e to the x, it is definitely a continuous function wherever it's defined. Similarly, 2 minus x is a polynomial. It's also continuous with respect. So each of these are continuous on their own domains. The problem is when you switch from one piece to the next piece, are they matching up or are they disjointed? So let's look at x equals 0. So I'm going to check the three things. First thing, is f of 0 defined? Yeah, I'm going to pick the piece where x is equal to 0 and then plug in 0 for x and get e to the 0, which is 1. Check. 2, the limit as x approaches 0 of f of x. Well, usually, although not always for these piecewise functions, that's going to involve taking the left-hand limit and the right hand. One of them we probably already know. If we look at the limit as x approaches 0 from the right-hand side of f of x, that's going to be the limit as x approaches 0 from the right-hand side? Well, I have to use the piece of the piecewise function where x is just a little bit bigger than 0, which is going to be the middle piece here. To take the limit, we plug in what x is approaching, we get e to the 0. We're not surprised to get 1. But then we also have to check the other side. The limit as x approaches 0 from the left-hand side of f of x. And then we're going to use the piece where x is less than 0. So that's going to be the limit as x approaches 0 from the left of x squared plus 1, which is 0 squared plus 1, which is 1. So since the right-hand side limit is 1 and the left-hand side limit is 1, the overall limit as x approaches 0 of f of x is also equal to 1. And then people often forget to check this third part, but it really is important because sometimes these are different. But the third part says the limit as x approaches 0 of f of x must equal f of 0. And it does, because they're both equal to 1. So in this case, f of x is continuous at 0. Let's see what's happening at 1. So at x equals 1, same deal. First, we're going to look at f of 1. And we're going to still plug it into the middle piece because that's where x is equal to 1. And we're going to get e to the 1, which is just e. Which you don't need to write more, but you could tell yourself is approximately 2.7. But really, that's all we need to write. Second part, the limit as x approaches 1. Again, we're going to look at each of the one-sided limits. So the limit as x approaches 1 from the left-hand side, we're going to use where, we're going to use where x is just a little bit smaller than 1. So that's still going to be the e to the x part. That's the limit as x approaches 1 from the left, e to the x, which is e to the 1, which is e. And now on the right-hand side of 1, as x approaches 1 from the right of f of x, we're going to have the limit as x approaches 1 from the right of, well, when x is bigger than 1, our function is 2 minus x. And if we plug that in, we get 2 minus 1, which is 1. And those two numbers are not equal to each other. E is definitely not equal to 1, which means the limit as x approaches 1 of x does not exist. And we're done. We get to say the function is discontinuous because one of the three things failed to be true.
For the top one, do you have to use e to the 1, or could you also use 2 minus x?
No, we have to use e to the x because when x is equal to 1, the function is defined to be equal to e to the x. It's not equal to 2 minus x. So graphically, here's what this is going to look like. Graphically, we have x squared plus 1 to the left of 0. So here's our parabola on the left-hand side of 0. And then we have e to the x from 0 to 1, which kind of looks like filling in this point here. And then we're going up to here. That's the point 1 comma e. And then after that point, we have the line 2 minus x, which is going like this. So it's discontinuous at 1, it's continuous at 0. It's also continuous everywhere else. So if we wanted to say where is it continuous, it's continuous on the interval from negative infinity up to 1, exclusive of 1, and then everywhere from exclusive of 1 to infinity. That is all the time we have. Make sure you got your name on the attendance sheet, and I'll see you on Thursday. I have office hours over in CADS right now for the next hour.